Okay, continuing from the previous video where we built a binary that we run on the Brave Large with the two functional blocks, let's now modify the second functional block to make it run actually on the FPGA. So we relaunch the Space Creator, and in the configuration of the function2 functional block, we see that there is actually, in addition to the other properties, there's an FPGA configuration one. What this means in the context of the Space Creator is that I want this particular functional block's logic to exist in FPGA form when my mission is in a specific list of modes. So imagine that you want the FPGA to host a bit file that during launch and during mission mode A, whatever, the function2 block needs to exist as a hardware component. But in the others, it can be a software component. Then you would enumerate here a list of the modes where you wanted it to be in hardware mode. In our case, we want the function2 functional block to exist as an FPGA in all modes. This is a magic keyword, so to speak, that the direct stays to tell, okay, translate this block's code into a hardware description, and always use this one. So basically, always communicate with the FPGA whenever you want to invoke the interface add two numbers in this case, hosted by functional block 2. So now that we've done this, and I save all, of course, as always, I go back to my deployment view and I perform a compilation again. Now, there will be some differences now. First of all, Taste will create additional things, additional device drivers to speak to the FPGA, but also you see here that it invokes Bamboo. Bamboo is a high-level synthesis toolchain, an open-source high-level synthesis toolchain that translated, as we during the build, it translated the code of the function2 functional block into the semantically equivalent VHDL definition. So let's have a look actually in what exactly happened during the build we just did. So I will go into the work folder again, and I will do another update of my tags so I can navigate with my editor, and I will go under function2 in the C wrappers, and I will check what Taste generated for the add to numbers interface in terms of the VHDL parts. So first of all, we see that there is now a function2 add to numbers FPGA function automatically generated, and within its body there's a part where we convert the input parameters into basically register write accesses that communicate the inputs to the hardware side. Then we tell the FPGA, okay, I've populated your inputs, wake up and execute the actual logic. And when the FPGA tells us, okay, I'm done, we go and read again of a register accesses the outputs and populate the result to communicate it back to the software side, to communicate it to whoever actually invoked the call of the interface. And to see what actually happens during these conversions, I'll go to the first one of parameter 1. You see that first of all, we dereference the passing pointer. If you remember, in the description of the interface, we said that we are using native encodings. This is where you see this in action. So basically, because we're using native encoding, so there's no actual ASN1 encoding taking place, because both functional blocks exist within the same processor. There's no need to encode and decode for no reason. We just dereference the pointer and we get the value. And then we use the value, the var my integer value we just read from whoever called us, to populate through a series of I/O writes, to populate the proper registers on the hardware side. And you see that we write in a particular offset, so a base address plus 8 for the first parameter. For the second parameter, it is plus 16, hex 10, and so on and so forth. So basically, Taste having full awareness of what our designs are using in terms of inputs and outputs, allocates them on the register space, and creates the device driver automatically to communicate with them at runtime. And notice that, okay, in this case we are using integers and it's simple, but imagine what happens when you have a structure containing, multiple fields and other structures and arrays of structures. The complexity there explodes. Well, taste handles all this complexity completely automatically. And if you go and create a design and then you realize, oh, I forgot something else, and you go and put it in, automatically taste will create both the device driver and the VHDL skeletons for it. And when these conversions are complete, then the execute add to numbers function takes over, and you see here that we write on offset 0, which is obviously reserved for this, let's say, signaling of the go ahead and start message. The FPGA side will wake up, it will start do its processing, and when it is done, it will notify us through another offset 4, that, okay, I'm done, go ahead and read the results. So basically in this proof of concept implementation for the Brave Large, we are using polling to communicate with the automatically generated FPGA side. So this is the core logic in terms of the C side of communicating with the FPGA. Let's look at the FPGA side, which is in VHDL on C sources. No, not here. Wrappers, sorry, wrappers, HDL. So first of all, there's a synthpy script, which is the entry point for the NanoExplore synthesis toolchain. So basically, if you have installed and have a license for the NanoExplore synthesis toolchain, you would do nx python synth.py and it will run. I don't have one in this VM. This is a pristine Tastemaster VM, and we don't have yet a license to have the NanoExplore synthesis toolchain packed inside it, installed inside it. I hope it will be happening in the future. But in any case, if you do this, you will get after a while that the synthesis will complete, and you will get a working bit file that has the complete implementation of the function2 functional block inside it. How does this happen? Well, let's open up the generated sources. So in the APB taste IP, we have we can see that there is a skeleton here generated, where the component, the hardware component, has, first of all, the usual, there's a clock and a reset signal. Then there's the two sentinel signals, so to speak. So basically there's the start signal that the device driver sets after it has populated all the inputs and raises a flag telling the FPGA, okay, go. Now you can start processing. And when the FPGA side is done with its logic and it has computed the outputs, it says, okay, I am done. And it erases the finish flag. After, of course, it has populated the corresponding outputs. In our design, if you remember, we had P1 and P2 as inputs and P3 as an output. Now, taste doesn't just generate the skeletons and the APB parts necessary to make this taste APB peripheral operational. It also, as we saw during the compilation, invokes Bamboo to translate the C source code of the functional block into the corresponding VHDL. And if we go here, you see the add two numbers Bamboo VHD, which is automatically created from the Bamboo compiler, that took the code of the function2 functional block and translated it into equivalent VHDL. So I am no hardware expert, that's for sure. So I just looked for plus, to be honest, and I'm pretty sure that this is the place where Bamboo actually translates the original code doing the addition, because Bamboo compiled the C code of function2, the add two numbers function inside the function2 functional block, and when it compiled it with LLVM and built the abstract syntax tree, at some point it had a plus expression, and you see here that the plus expression part of the AST got translated eventually into the corresponding addition. And of course, there's plenty of code here. I'm nowhere near understanding everything here, but I don't have to. That's the whole point, that this is a compiler built by the Politecnico di Milano that translates the C code into VHDL. At this stage, I could do the same thing I did in the previous video and take the generated bit file and run it with a new binary, because when we build also we got a new binary. But I won't do that because, quite frankly, there is no difference. From the taste point of view, the application doing the call, the thread doing the call from the pulse function into the add two numbers sees exactly the same behavior as the one it sees from the C implementation. The only difference being that now we are doing this from the hardware side. And I don't know if you noticed it. I closed the taste. That's okay. I'll do it again. I don't know if you noticed it, but the stack usage was higher because the device driver itself also does has to reserve some space to do its work. And in fact, maybe this is a good time also to show that all the stuff we do from inside the IDE can also be done from the command line. So if I do this, you see that the function one pulse, which used to be 330 something bytes, now is 488 bytes. It uses a bit more stack because it has to communicate information across to the hardware, and there's a series of calls to functions that populate the registers and all that. So that's it. That concludes the set of videos we wanted to prepare to show you the work done to support the Brave Large from within Taste. Thank you for watching.